Hello, good afternoon, everybody, at least for the participants who join us in Europe, and welcome to the first session of the EU for Agriculture Under Pressure workshop. My name is Bettina Baruth from the Joint Research Center of the European Commission, and I do co-chair this session with Hans-Jörg Lutzeyer from RTD. The session and the topics are grouped under the thematic area of the environmental impact in the context of the European Green Deal and its farm-to-fork strategy. We will have 5 presentations, and we think we have a really interesting mix to cover this topic, from more operational application towards research study character applications. Each presentation will be around 15 minutes, followed by 5 minutes of question and answers. And to conclude the session, we will have another 20 minutes to answer to your questions. Before we open now and give the floor to the first speaker, I'd like to hand over to Hans-Jörg, who is my co-chair, to introduce him. Thanks a lot.
Thank you very much, Bettina, for your opening words. Warm welcome also on behalf of DG Research and Innovation from the European Commission to this important and very interesting first session of this week's conference. I will serve as a co-chair together with Bettina today. And just a few words. So I'm working in the food systems team of DG Research and Innovation. I'm in charge of the Standing Committee on Agricultural Research, the Food System Partnership, and also EU-Africa collaboration on food and nutrition security and sustainable agriculture, where we have important Earth observation components. You are all aware of the farm-to-fork, the Green Deal, the farm-to-fork strategy, and also Digital Europe, which are guiding policies for us in developing Horizon Europe, with important components of Earth observation and also a partnership in the making of agriculture of data, so a partnership agriculture of data, and which will be introduced together with strategic planning of Horizon Europe on Friday, in the Friday session, by Marian van Merlo of DG Research and Innovation and Doris Marquardt from DG Agriculture. Therefore, I don't want to give you more overview on Horizon Europe planning, but jump directly into today's session and giving the word to the first speaker on insights from Europe's first national-scale CAP monitoring system using Earth observation, very much already in the spirit of a partnership of agriculture of data. So over to you, Kenneth, it's your turn.
Yes, thank you. You should see my presentation appearing, maybe. Oh, hold on here. We go. Can you see my presentation? Can you give a nod if it's in the full screen?
Yes, we see it. It's
okay,
fine.
Very good.
But you see the moderator view.
Okay, I'll just change that. Perfect. You should see it right now, okay?
Now it's perfect, thank you.
Okay. Yes, so my name is Kenneth Grogan. It's my pleasure to be the first speaker. I'm working for a company called GRAS, and together with another company called NEO from the Netherlands, we've been working with the Danish paying agency to develop a CAP monitoring system in Denmark. So Denmark is one of the countries that really went all in with the technological solutions to CAP. So they're replacing the traditional on-the-spot checks with a fully 100% satellite-based system, and it was us that has developed that over the last 3 to 4 years. So it's a fully end-to-end system in that it goes from raw data to results being displayed on a screen in near real time. We starting here from left to right, we have the back end or the satellite data processing. Here we use Microsoft Azure to crunch all the data. We then store this in a parcel SQL database, and then we have we're experimenting now with data cubes for the grid-based data. Our analysis is mainly driven by Python, Keras, and TensorFlow, and then we have a front end where we update all the results as they come in on an interactive web viewer. So the workhorses, this is mainly what is driving everything. It's mainly the Sentinel data, of course. We have Landsat 8, we integrate. We mainly work with time series analysis and machine learning algorithms. These are the core analysis tools. And then we have, I would say there's more than this, but there's basically 6 themes that we try to monitor. And these are crop classification, detection of ploughing, harvest detection, grassland activity monitoring, and then there's also cover crops or catch crops, and finally this boundary parcel or the boundary validation. So I just want to give you an example of one of the workflows of the basic payment system. So this is it's working on the traffic light system. So this is green for compliant parcels, red for non-compliant parcels, and then if there's insufficient data, they get a yellow color. But this workflow would start, say, from the machine learning perspective. We classify all the crops that the farmers have declared, and then when the crop is classified as an annual crop with high probability, this will of course get a green color, and then if it's classified as grassland with high probability, it enters this processing chain. So we would, so let me see here, if it's detected as an event, so it gets a green, but no event, it goes into this extra little bit of analysis here I want to come back to a little later, but it's a non-compliance probability, and then it goes on to expert judgment and is again given one of the traffic light colors. If we have uncertain crops, so it's classified with low probability, then it enters another stream where we monitor for different activities, so harvest, ploughing, or even grassland activity, and these activities, if detected, get green, and similarly the other color, it follows the expert judgment if there's no event detected. And I just want to bring you through some of the things we do then. I won't say much really about crop classification. I think there's some other presentations coming up later about that. But what I will say is that we're using the full time series with Sentinel-1 and Sentinel-2 and Landsat. We're very happy with our results here. So we have overall accuracies around 93-94%, and all the major crops have well into the 90s for accuracies. So I think I'll leave it to someone else to talk about that in one of the later sessions. What I do want to talk about is something about time series markers, and yeah, so we do a number of these, as I said, for harvest, ploughing, and grassland activity. We use a number of different time series streams to detect these activities. So here in this bottom panel, you can see the coherent signal, and in the black line, and then we have the dots are from the optical signal, and this is on our web viewer, which the Danish paying agency has access to and can get updates on a daily basis. So here we can see an example of a harvest event in August this year, and then you can pop up some image chips, and you can see okay, when does this event happen, and confirm that it is the case. We, in this near real-time system that we have, we are reporting the time series markers in an individual basis. So we just say, okay, Did it happen in coherence? Did it happen in the optical time series? But it got us thinking, okay, how can we combine these markers? We think there's some room here for an elegant way to combine time series markers. So one advantage of this would be that it would be more robust against false detections from any one sensor. You would also get more confident predictions. If one marker backed up another, then you can be more confident. You can also use the timing of the different images to narrow down the time interval when something actually happened. So that's something we've been working on here. This is an example of a maize harvest. Here in the top 4 panels, we have different streams or different time series. The single look complex data. This is the omnibus statistic. We have the backscatter. We have INSAR coherence, and then we have the optical time series here in the 4th panel. And what we do here is convert each of these change magnitudes from each stream into a different into a probability, and then we combine them based upon a weighted probability, and then we can use logic then to narrow down this timing interval. And this we have found to be one thing is more accurate, but you also get a more accurate time interval by using all of these data streams. We also do grassland monitoring. So again, it's similar to the harvest markers. Here you can see an example of a parcel which has been mowed 3 times in the season this year, and this is also evident in the optical and coherence time series. There's one thing that we have to be a bit careful about when using the optical data, especially when reporting in near real time, and this is the cloud masking. So this is one of the common issues. Of course, everyone is struggling with this to some extent. So this is an example of this season's time series for this parcel. You can see in the monitoring season, there's about 28 optical observations here, and there is 3 of them that are not great quality. 2 are affected by haze on either side, left and right, and 1 is cloud. And these can, of course, mimic some activity in the field, so they mimic a disturbance. So we have to be a bit careful in reporting these kind of. We have to be conservative in the near real-time monitoring system that we don't report these. So we only report very sure cases in our near real-time monitoring system. But yeah, it's just to say, even if you have a very accurate cloud mask, say 95% accuracy or above, generally you'll still get 1 to 2 that have been affected by atmosphere. So it's really a critical part of monitoring. Another thing that and another important point that I think is not getting enough attention is this issue of unbalanced classes. So generally, Danish farmers are really compliant. So we don't really know what the distribution is of non-compliance, but I was just talking to the paying agency this morning. They think it's less than 1%. Here I give an example of 2% non-compliant, and we want to see how this affects like accuracy statistics. So if we look at the guidance from the JRC, they give a guidance for 5% type 1 error and 10% type 2 error, or this is the same as saying the producer's accuracy of 95 and 90% for these 2 classes. But what this doesn't really address is the user's accuracy, and this is what is really important from the paying agency's point of view, the user's accuracy of the non-compliant parcels. And this is very much dependent on the distribution, the real world distribution. So I'll just walk you through this very quick example. If we have, assume we have 200,000 grassland parcels, and here we see they're divided up, as I said in the previous slide, 98% compliant, 2% non-compliant. And we have the accuracies of 95 and 90%. We can see that the models are performing very well, and we have an overall accuracy of 95% here. But look at the non-compliant accuracy, and here the user's accuracy. Here it's 26 or 27%. So this means even with an accurate model, because of the very unbalanced classes, you will get an extremely low user's accuracy. You know, the fact is this is saying 2% here, but in reality it could be 0.5%. And then again, with this very same model, you will get a user's accuracy of non-compliance of around 10%. So this means if you were to do it in an automated fashion, right from just with a very accurate model, that you will get 1 in 10 of these non-compliant reds incorrect, and that's just caused by the class imbalances. So what we do to address this problem is we have this extra step in our analysis called non-compliance probability, and here we use a combination of machine learning and time series analysis to give a combined score, probability score of non-compliance. The advantage of doing this at the end is that you have all of the data from the season from each parcel, so you can have an estimate, have a better estimate of the signal to noise, and yeah, it's just we have the full amount of data, so we can do more things with that. The first part of this machine learning, yes, this is based upon, again, inputs from Sentinel data, and is trained on past control parcels, and this outputs a probability of non-compliance. The second part here, it's a time series analysis, but it's more thorough or rigorous compared to the near real-time monitoring. And here we have adapted this from Griffiths et al. So just walk you through it here. We fit a convex hull over the upper envelope of the time series, and this gives us a model of the phenology throughout the year. And then we look for deviations from this modeled phenology, and if there's above a certain threshold, we say it's compliant. Here we can see 2 events detected from this example from Griffiths et al. And here's an example of a non-compliant parcel. So there we don't see much deviation away from this idealized curve. What we do then is turn this into a probability. So we use this change magnitudes and a logistic function to estimate the probability of non-compliance, and then we combine that. So it's this step with there's a machine learning model and a time series analysis model, and we combine these two to get a better handle on the non-compliant cases. So this, in effect, increases the user's accuracy of the non-compliant cases by ranking them using these models. I've just actually finished this analysis today, and the Danish paying agency will be sending out the red notifications, I think, already tomorrow, and then the farmers will get a chance then they'll get, I think there's another 3 weeks left in the season, something like that. They get a chance to either prove that they are compliant, or they actually have a chance to mow their grass and be compliant. And just some closing remarks. These, as I said, these extremely unbalanced classes have the potential to make remote sensing solutions be perceived as poorly performing, even though they are actually good models. Combining multiple markers, we've experienced that it's a good thing to do and can lead to more improved results. And also, just in general, a general comment is that the monitoring system is being well received by the Danish farming community in general. We were quite worried that, okay, they'll think, oh, they're being monitored and we'll find out exactly what they're doing. But it's actually, they like the fact that they're not getting on the spot checks very often, and they're actually happy with this automated system that they can also follow and get a chance then to be compliant through these early notifications. I tried to squeeze all of that into 15 minutes. I hope I was close. I just say thank you to everyone out there.
Thank you very much, Kenneth, for this exciting presentation and for keeping the time. We have time for one question from the audience. So we give it a try, actually, while the big discussion will follow at the end of all presentations. If there's one question popping up. Okay, if there is no immediate question, maybe people have to get used to this possibility of asking a question after a presentation. Thank you, Kenneth. Very interesting presentation. And I would like to hand over to Bettina to introduce the next speaker.
Yes, thank you very much. And thank you, Kenneth, again for this presentation. I liked especially, or I found it very interesting, your feedback with the shift from the controls to the monitoring, that farmers perceive this as something positive, that they get these early warnings. We stay now in the topic, and I'm very happy to welcome Pierre here in this session. He will report on the Sen4 CAP experience they have in support to the new CAP reform. Pierre, the floor is yours.
Thank you, Bettina. Thank you very much. On behalf of the consortium, including GISAT, CS Romania, EGO, Synergize, and led by UCLouvain with Sophie Bontemps, it is my pleasure to share with you the current status of the Sen4 CAP open source system, which has been designed and used for continuous near real-time agriculture practice monitoring, very much in the same line than what Kenneth has shared just now. This has started on the request of DG Agri, with a close collaboration with GRC and DG GRAS, and as a ESA project. The idea was to prove some evidence using Sentinel-2 to support the CAP, and in particular the CAP monitoring. I will not focus on the overall project. I would like to update with the most recent achievement and result. I will come back to the content of Sen4 CAP system in my second part of my talk, as many of you has probably heard a lot already about this project and system. Sen4 CAP is a project which is turned into a toolbox today, an open source toolbox, starting in 2017 with local site to define use case, allowing to develop a specification for product, and then algorithm and system. This has been demonstrated at national scale in 2018 and 19, and the fitness to use was assessed by the paying agency, which were involved, 6 of them was involved from the beginning. And today we are in the user uptake and the system evolution. I will come back to that in detail later. Therefore, what's going on 2020 season? The 2020 season is let's say an add-on. It was not planned in the ESA project initially, but the country has requested to continue the work, and therefore Netherlands and Italy are currently operating the system for themselves with the support of the consortium just for capacity building and system adjustment. Spain, Castilla and Leon, more specifically, are using the classification module in their own integrated system for monitoring, and they do that on their own as well. While Czech Republic, Lithuania, and Romania ask us to operate the system for them, and they are focusing on the fitness to use for their own purpose, and we customize the production along the season specifically to their criteria, as for instance for Lithuania with a very rigorous time step delivery. Last but not least, France is spending much time to have a deeper validation of the 2019 product. This is what was going on for the 2020 season, being, let's say, the handover season after the 2018 and 19 demonstration season. In terms of uptake, we are with a wide user uptake today with 260 downloads of Sen4Cap, with many of them per countries. This is within 12 months, and we deliver in November 2019, and this has been downloaded by many users. More than 20 paying agencies are currently testing on virtual machine Sen4Cap to assess its fitness to use for themselves. And this has been run on CryoDias thanks to the ESA support. And actually, last but not least, DIAS is offering Sen4Cap as a service. On the other side, a wider uptake has been also observed in the context of the NIVA project, as the NIVA teams has been requesting to be trained on Sen4Cap, and they are using Sen4Cap markers to develop new agri-environmental indicator. Indeed, their ambition is to turn the Sen4Cap not only for the first pillar, but also for the second pillar. And for instance, 2 or 3 new indicators are under development. The carbon budget, as you can see on the illustration here, CESBio has developed a carbon budget at parcel level, and actually they are planning to develop this as a Sen4Cap module. There is also the biodiversity and nitrate leaching risk, which are the 2 other indicators set as priority by NIVA. In terms of capacity building, a large effort has been put on this through webinar with sometimes up to 150 participants. There is an online forum, and of course, this is an active forum with almost 500 posts since a few months. And finally, for the capacity building, we have organized a training hosted in UCLouvain, where 44 participants coming from 20 countries were attending, and all the resources are available online for those who want to invest. Another training was planned for the Pantarei, but it has been postponed, as you may expect. Okay, this is what was done for 2020. And just to recap, for those who are just listening for the first time to the Sen4Cap system, the Sen4Cap system has been designed as an open source and automated and modular system, and it has been demonstrated for near real-time or offline production, either on cloud or running locally. And as you can see here, it's not only the initial processor, but you can see that there are 2 new processors related to the marker database and to the tillage detection processor. Because Sen4Cap being open source, we expect that this is evolving very, very dynamically. Sen4Cap, is actually running as the data are acquired, and as I just mentioned through the graph, it handles all the input from Sentinel-1 and Sentinel-2 and combine this with the parcels and then pre-process all the imagery into markers. Therefore, this is about 50 markers per week, which are recorded into the database for each parcels. 22 markers coming every 10 days from Sentinel-2, and 20 markers coming every week from Sentinel-1. And therefore, this is cumulative over the season. Those markers are kind of metrics which allow actually to assess the activity and the agriculture practice along the season. What is the novelty of the 2020 effort from the consortium perspective is actually the development of the marker database. Indeed, while Sen4Cap was first designed to address specific use case, the paying agency requests to have a much more flexible environment, allowing to take advantage of all these markers on their own, with their own approach. And therefore, it has been developed a marker database, which is accessible through the Sen4CAP user interface, as usual, but also by any other API application, which can address the marker database, or even so, some user could directly address the file, not going through the database for very specific development. Therefore, this system will be released as a beta within the consortium in a couple of weeks, and will be probably available by December or early next year as a new processor for Sen4CAP. It will change completely the way Sen4CAP can be used, because all the metrics, all the markers will be available for the application that the paying agency is looking for. The initial use case, which was selected from the very, very beginning to develop the overall system, was the 6 use case here listed as a crop diversification, grassland mowing, IFA fallow, IFA catch crop, nitrogen fixing, and land abandonment. Of course, I will not go through all in this detail. Kenneth did a good job to show already some example. We'll have some others. National crop type mapping, as you understood, it has been running for 2020 season again. This is the example for the Czech Republic with 60 crop types, which were recognized with an overall accuracy of 90%. 99.5% of the area were assessed. And this allowed to compare the declared crop type with the predict crop type with a certain confidence level, and to make the diagnosis about the conformity assessment. Of course, the conformity assessment takes into account not only the predict crop type, but the second predict crop type, and so on. Even more specifically, the Spanish colleagues actually consider that they should use more than just 2 crop types, and I think this is the Netherlands who use 5 crop types and the user confidence for each of the 5 top crop type which was predicted to assess the conformity. In 2019, 600,000 square kilometers were assessed with 15 million of parcels, and this is a kind of overall accuracy and F1 score that you can get along the season. This is here displayed for Lithuania, where you can see that by June you get already a very nice score in Lithuania for many of the land cover, the crop. Of course, for the small parcels, we have also to address this in a very specific way, and therefore additional classification based on Sentinel-2 marker allowed to minimize the impact of the parcel size, and so on. Therefore, this kind of activity is growing, and we are really learning by doing and by repeating year after year the adjustment and a better understanding of the limitation allowed to fix and to adjust the parameters. Of course, as you know, it's not because you have a predicted crop type that you can just rely on that. You can also look at the biophysical indicator to further investigate the crop type label, and you can assess the profile and look at the probability to have an agreement with a standard profile for the given crop type. Regarding the mowing detection, we use Sentinel-1 and Sentinel-2 exactly like Kenneth mentioned, probably not exactly the same algorithm. And this allows, of course, to detect the mowing event. It's neither only Sentinel-1 or Sentinel-2 which detect the mowing event. This is a combination of both which is necessary, allowing to generate the mowing event detection as a table for each grassland, permanent grassland in the area. Regarding environmental focus area monitoring, here you can see the coherence in VV, the backscatter ratio, and the NDVI, which is going on. And along the season, as you can see, there is 10 markers, and at the beginning they are all set as false, and along the season they are turned into true on the left side, on the right side of the slide. And when they are all becoming true, I mean, the compliance index is turning into a level of confidence. In this case, this is strong. This is for the harvest of a catch crop. The detection of the harvest of the main crop and the catch crop monitoring. Oh, sorry, this is too quick. A new processor next to the database development is about the tillage and the no-tillage detection. This has been developed in collaboration with Lithuanian and Spanish colleagues. One is regarding the tillage after the harvest of the main crop, and the other one is the tillage within the fallow land period. And this is mainly based on NDVI, the backscatter ratio, and the coherence in VV, exactly as the previous example, to detect the plowing event in these two contexts. This it will be also released with the database marker database in the new version of Sen4CAP. Maybe you heard about the GRAS initiative from the Commission and the European Space Agency, where at the beginning of the COVID crisis, they considered that we should use Earth observation to fulfill a dashboard platform to assess the impact of the lockdown. And a major concern was the harvest of the main crops, the staple crops, with some concern about the supply of spare parts for the machinery, and therefore a request was to assess the harvest in Spain for the winter cereal, and therefore we use the Sen4CAP system to monitor in real time the harvest progress over the whole Spain area with the 5 markers that you can see on the slide. And therefore, along the season, since April, we have been monitoring that. But before to do so, we processed the year 2019 to have a reference. And therefore, we have the reference of 2019 harvest progress as a benchmark. And then we assess along the season the 2020 harvest progress for the winter cereal at the different administrative level. Here it is displayed at the level of autonomous region. And we can say today that the season has been great. It was a very good production with very good yield, unlike 2019, which was actually a very dry season. And this is why there is such a shift in between 2019 and 2020. It was much more related to the meteorological condition than the COVID situation. Just to conclude, I believe you understood the Sen4CAP open source system is available to all. It can be turned into a database to use the marker, which are derived along the season on a regular basis at parcel level from Sentinel-1 and Sentinel-2. And this allows a near real-time production or offline production if you want to play again a previous year. The Sentinel marker and the EO product usefulness has been assessed at national scale by 7 countries for 3 years. Therefore, this built some capacity within the community to understand the shortcoming, but also the full potential of that kind of approach. And the very good news is the fact that the Sen4CAP system will be maintained in the long term in the context of the ESA Agriculture Virtual Lab. And therefore, we are sure that the system will be continuing far beyond the project. The wide uptake of the Sen4CAP module actually requires this kind of long-term horizon. As you have seen, more than 20 paying agencies are currently playing with the system. But this is only the start. I mean, all these markers are opening the floor for new applications, supporting more sustainable agricultural practice for sure, and there are many more to be invented. Thank you for your attention, and thank you to for the contribution of the paying agency and the consortium member.
Thanks a lot, Pierre. Thanks for keeping the time, and thanks for the excellent overview. And it's really interesting to see now the wide distribution and the take-up of the system by the paying agencies. And I'm really interested to see the results of the fitness for purposes test. We have now one question which relates to your last slide, namely, what is the ESA Agricultural Virtual Lab? And before you answer, I would also highlight that there's a Slido window in the application where everybody can pose questions, and then we will receive them and can ask the presenters. So what is the ESA Agricultural Virtual Lab?
ESA has developed a virtual lab in the past. I think there is one for the marine application, and this is built on ESA computing infrastructure, which is first dedicated for R&D activities. I mean, allowing the researcher to get access to many data sets and to tools. Sen4CAP will be one of these tools, as Sen2Agri and others. Sen80, for instance, will be there as well. And therefore, because they are part of this environment, they will be maintained. And of course, they will be also subject for improvement and research R&D activities.
Okay, thanks a lot. I would now pass over the floor, if there are no more questions, to Hans-Jörg to introduce the next speaker. Hans-Jörg, you are still muted.
Okay. So introducing the third speaker, Raphaël, on a Sentinel-1 based European crop parcel map using 2018 in situ LUCAS Copernicus observation. Raphaël, over to you.
Thank you. Good afternoon. Can you hear me well? Yes. Okay, just to be sure. Okay, so it's my pleasure today to present you a common work effort with my team. So the name are here, but I want to really highlight that it's a really team effort. And the title of the talk is a Sentinel-1 based European crop parcel using LUCAS Copernicus data. So, okay, first of all, some context. I think that several points don't need to be here because the two presentations are in this way. But first of all, the Copernicus and processing at the scale is for sure transforming the common agricultural policy. And we know that about half of the EU is farmed. So this is a really important leverage to develop policy at the continental scale. So we need today benchmarking of methodology in order to be able to apply them in the future, while the Copernicus program is guaranteed for the next 20 years. And as it was highlighted in the two previous presentations, the paradigm shift now for the monitoring, meaning checking if the compliance of the parcel using Copernicus data is quite well ongoing. But at the same time, we have also higher and accountable environmental and climate ambition. So this is highlighted with the new Green Deal and the Farm to Fork strategy. Therefore, performance monitoring and evaluation of the CAP strategic plans is becoming one of the key priorities. We have to develop methodology in order to retrieve indicators for reporting at different levels. And this is one of the reasons of the work I will present today, where we, thanks to a case study, want to assess the contribution of Copernicus to develop new CAP impact indicator. And in fact, we want to do this at the parcel level, but consistently to the continental level. So in order to introduce our work, I will first introduce you an important data set that we've used. Very of you are familiar with LUCAS. So LUCAS is the Land Use Cover and Area Frame Survey. It's an important effort of in-situ data collection over the EU. So there were 5 main campaigns so far, every 3 years, from 2006, 9, 12, 15, and 18. It's a lot of surveyors and a lot of logistics to send the people on different points over the EU. And at the end, we have 1.3 million of points that were collected. So we did a huge effort to harmonize all this data and to document it properly to be usable for scientific publication. And you have a paper now that was accepted last week, basically, where we are providing in open source an harmonized data set. What is really important to notice here is that the design of the LUCAS was not done for Earth observation. Then we have some caveats there. And to tackle these caveats, a new module was introduced in 2018. It's called the LUCAS Copernicus module. And in fact, for some of the points, so every survey of LUCAS, it's more than 300,000 points. For some of the points, a new protocol was applied. So I don't see if you see my mouse properly here, but let's say that you have a typical LUCAS points here as highlighted on the figure here in red, where you have 1.5 meter buffer, meaning that you have a subsample of a typical pixel of 10 meter. In the Copernicus module, in fact, instead of recording the in-situ land cover and land use at a given points of 1.5 meter, you record it for a full polygon up to 100 meter of diagonal. At the end, it was planned for 90,000 polygons, but it was possible to do it properly for about 60,000 polygons with an average of about 30 pixels of 10 meter. This data set also, we have published this, and it's now in open discussion in ESSD, so you can download the data. It's still in open review, so if you have any comments, feel free to comment it, because it's the end of the reviewing process so far. What is the result of this is that we have about 60,000 polygons, not pixels, but polygons, really distributed spatially over EU, in 66 land cover classes and 38 land use classes. And what is really exciting here and relevant for the work we've done is that, as you can see here, you have the crop type information. So again, it was not designed for Earth observation. So the legend is not properly designed if you want to do a pure land cover map. But with some work on it, you can do really amazing stuff. And this is what we've done. So to do that with L1 data, because it's the most consistent data that you can find at the EU level and national level. So we did some pre-processing on Google Earth Engine in order to have 10-day average for VV and VH sigma. So we did that for 2018 for this benchmarking. Here you have an overview of the consistency of the data over EU and on 2 specific places. And we have extracted the time series. First of all, one of the study goal was to see if Sentinel-1 time series, along with Sentinel-2, could be used to derive crop-specific land surface phrenology. And thanks to a study led by my colleague Michele Meroni, I will just briefly explain with an example. For example, for a typical LUCAS Copernicus barley polygon, we extract the Sentinel-1 cross ratio, the Sentinel-2 MDVI, and derive from the time series, we derive metrics such as start, peak, and of the end of the season. We compare the day of these metrics for Sentinel-1, Sentinel-2 with ground true phenological observation of Germany. And we do this for all the polygons. So this work is under review. Now here you have the reference, but it demonstrates to us the potential of using such data sets to go further a bit and to try to develop the topic of today, which is a crop type map. And for this, we had to start with defining a legend properly. So on the right, you can see the legend. for which we have more than 20 classes. Again, the legend, we are limited in the way that we have to use LUCAS data, but the legend is quite detailed, as you can see. We've used the training data set, so the 60,000 polygon, and then we've done some benchmarking with different types of models. I will present some of the results afterwards. Basically, we have trained a first model, so it's random forest hierarchical model, first of all, to define land cover. And then within the crop class, we went to the crop type. So you have here common wheat, durum wheat, barley, rye, oats, maize, well, all the classes that are here. So we did a benchmarking for different Sentinel-1 indices and also to detect the best temporal window in order to apply the classification. For validation, we've used the LUCAS in-situ points, so meaning not the polygon, as I explained today. It's really different. We have about 100,000 points, and we've used also the farmer's declaration where it was available. So the result of the model benchmarking, we've used more than 1 million of time series to generate this, that we've tested different models. And over our 4 biomes, basically, we've trained 2 models for each biomes, one for the land cover and one for the crop types. We show basically from the results that it was the best to use VV and VH in order to maximize the accuracy. So we've compared with VV, VH, the cross ratio, both, everything together. We also test the RVI, and that was the result of our benchmarking. About the temporal benchmarking, okay, temporal benchmarking here you can see. Maybe let's start looking at the map. You have different models trained until April, May, June, July. And here for 4 classes, for example, you see that basically your accuracy is evolving. If you look at the F-score, the same, you see that you can already well classify maize and wheat at the beginning of the season, but that's barley and sugar beet, you need to wait to have a bit more of information. So by testing all these models with different time window, we could define the best trade-off between timeliness of the availability of the classification and the accuracy of the product. This is why we decide to use data from January to end of July. And that's the result. We have processed about 6,000 tiles on the cloud internally, the GDPP cloud. And for each stack is 72 time stack based on the VV and VH 10-day average. And we have a legend of 21 classes with different crops. So if you look at some specific points, so I want to use these points, different regions. So absolutely no post-processing, no parcel data use. It's purely based on the result of the classification. And you see how consistent it is. Up on the left, you have Orléans in France, where you see the diversity of the crops. On the top right, you see the border between Austria, where you have this narrow parcel, and Czech Republic. You see that it's really consistent for both. On the left down, you have Castilla y León, where you see mainly the sunflower and the barley. And then down on the right, you have Romania, where also you see different, a mix of big parcel and narrow parcel. So it was just to highlight the consistency of the results. About accuracy, so be careful, again, it's not a proper accuracy assessment because the sample, it's not a sampling design as it should be, but it gives quite an interesting idea of the result we may expect. So we have an average accuracy of 73%. Again, to do this, we have used 100,000 points. But as I explained at the beginning, the points are could be a subsample of a pixel. So you may have, in fact, we may underestimate the accuracy, and the accuracy may be higher. So here you have the confusion matrix with the 100,000 points, and also we calculate the accuracy at the country level. You can see on the map. So you see that there is an heterogeneity. In the south of EU, we have we are a bit less accurate than in the north. So this is one of the key information. And then the second assessment was done really what we did in the last weeks using the farmer's declaration, so the GSSA. And for each of the parcel, as you can see here on the left, it's in Flanders, north of Belgium. We have extracted for all the parcel the majority class, and then we do a count with all the parcels. So we have done it so far for 5 regions or countries, which is more than 2 million of parcels. So it's not a sampling, it's full scale. And you see that we have accuracy from 92% to 54%. And this is probably and mainly linked to the size of the parcel that you have here. Like Slovenia, it's 0.7 hectare in average. And for sure, this is quite a limitation for this type of approach. But still, the accuracy is quite high if you consider that we've used a unique approach at the continental level based on in-situ data only and not specific to the country. The conclusion of this work was that LUCAS Copernicus module has a high potential for remote sensing. I still think that there is a lot to be done there, and we hope that the work we've done to make this data accessible and usable will profit to other scientists. The Sentinel-2 is the only Earth observation data source that provides consistency for automated processing at national and continental scale. So this is really a key result also of this, because here we are not using Sentinel-2. For sure, it could bring a lot of information also. And the last point is that this exercise that we've done, so establish a benchmark for methodological upgrades. For sure, we can improve algorithms, in-situ strategy, and sensor merging. So now the perspective of this work. Oops. We need urgently to have a Sentinel-1 level 2 production at the EU level, because here we have to do it on Google Earth Engine. There are a lot of improvements possible. Huh? Here we have used Sigma, but now we are working on a Gamma version. We can use Sentinel-2 to filter out some parcel. We can use furthermore the GSA data. For sure, a migration of this type of production should be done on DIAS. Now we are working on transfer learning, so applying the model on other years. And also, this is something I want to highlight, that thanks to this work, we managed to convince the Commission to pay for another Copernicus LUCAS module in 2022, and they will collect 150,000 points. So it's really a good news, I think, for the machine learning and the Earth observation community. And for sure, this could be a precursor for multi-annual crop rotation indicator. That is a key discussion in the CAP impact. I would like to thank you for your attention. And again, I like the fact that this is not my work. This is a really teamwork. And don't hesitate to contact even me or Astrid if you have any question about this. Thank you very much.
Thank you very much, Raphaël. And you received 2 congratulations and 2 questions from the audience. So the first question is, how did you derive the phenometrics? Which tool have you used? How did you smooth and deal with irregular observations? And the second, were you able to test consistency of your models over years, 2015, 2012? And again, congratulations, great piece of work.
Okay.
Did you get the 2 questions? Please,
I will start with the question. So the first question, I guess it's about the land surface methodology fitting. So I suggest for the question to contact my colleague Michele Meroni, because he has done this part of the work. And the second question, it was on my last slide about perspective. So we have not yet done it, but this is in the pipe for sure. The problem is to find good data for validation as well. But we want to basically apply the same methodology over other years, and that's why we have prepared all this framework basically to be able to produce this type of crop type map at the EU level for any years, basically.
Thank you very much for your answer. Then I would like to hand over to my co-chair, Bettina. Would you introduce the next speaker?
Yes, thank you very much. So now we are leaving Europe and we look at rice monitoring in Asia, but we stay with the radar data. And I'm happy to give the floor now to Thuy Le Thom to present regional rice monitoring in Southeast Asia. Please, the floor is yours.
Okay, so I'm Thuy Le Thom, and we move far away from Europe to Southeast Asia. And the title of the talk is Detecting Rice Inundation Status for Mitigation Measures. And this is a collaborative work between us at CESIO with the Japanese University of Tokyo and Chiba. And we have Group BO, JAXA, ESA, and VNSC from Vietnam as collaborators. So why we move so far away? Let me move this. Okay. Okay, why? Okay. Why we move to Southeast Asia? Because rice is one of the major state food of the world, and Asia, Southeast Asia, is where 90% of rice is grown and consumed. And with the growing global population, the rice demand will increase drastically in the next decade. And so the increasing, I have a problem of okay, and okay, the rise in the increasing rise in the next decade will increase also atmospheric methane. Here, the schema key from UNVISAT have shown in 2005 that the methane emission quite concentrated in Southeast Asia, and this methane emission now increased steadily until now, as you say, with the Tanso and GOSAT since 2009. Why? Because of the flooded rice system, comprising irrigated, rain-fed, and deep water rice. They emit significant amounts of methane. And methane is a very potent greenhouse gas that contributes to global warming. And here you can see that the agriculture sector here contribute at 30.5% in the global source of greenhouse gas emission globally. And rice is not negligible. It's equivalent to biomass burning and modern manual management, etc. So if we reduce the rice greenhouse gas emission, and then we contribute to reduce the global warming. So this was seen here by the mitigation potential drawn by researcher here. It's in megaton of CO2, equivalent CO2. And here you see in Europe, the irrigation potential is over the cropland soil carbon, about 60 to 140. And in Southeast Asia, it's just rice, 120. So if we can do something to reduce this methane emission, greenhouse gas emission for Southeast Asia, we contribute to the mitigation of the greenhouse gas of the world. And how we do that? First, we have to reduce the greenhouse gas without reducing the crop production. And it needs to be low cost, the implementation. We need to be in line with the government subsidies and easy to implement and not disturb the farmer way of life. So, and then the factor that affecting greenhouse gas emission, we need to understand them before to select the option. The factors: land preparation, seed preparation, rice varieties, crop calendar, fertilizer application, and water management. And from all that, the International Rice Research Institute recommend option is on water management. Specifically, it's to practice alternate wetting and drying. So it means that we need to have periodic drying and reflooding of the field instead of continuous flooding as is done until now. So the benefit is to reduce greenhouse gas, to reduce water consumption, to have low investment and being accepted by farmers. And the AWD practice are now spread over Asia and being adopted by advanced farmers and encouraged by national authorities. For example, here is the flyers distributed in Asian countries in different languages. And here, what is AWD and why to do, why it's important to have to save the amount of water. Here, 2,500 liters of water for 1 kilo of rice. And here, how it does work, it say that we need to flood the rice and then let it dry until -15. We can survey by the kind of tube, and then to refloat again. So it's reduced greenhouse gas, and benefit is also about the return of the money. The AWD has been based on a lot of research carried out since in the last decades, and but the research in experimental fields. And here our Japanese colleagues from the University of Tokyo and Chiba conduct a study on the farmer fields, the rain farmer fields in the Mekong Delta during 5 years and 3 crops a year. And then where they do measurement of, here is water level, red is the AWD, and blue is a continuous flooding. And here is measurement of methane emission, and with different way of practice with straw, ash, etc. And then the result after 5 years is really clear. Here is for the irrigation, we have a 30% reduction. For greenhouse gas emission, you have 40 to 60% reduction. And for the grain yield and the quality of the grain, it's slightly improved. Now, if the AWD is good as mitigation measure, what are needed for the government to apply it and to survey and to do the MRD, etc. So we need to have mapping of dissemination status of AWD. We need the real-time forecast of irrigation water demand in order to help the farmer community to declench the irrigation operations. And we need also to map spatial temporal methane emission. What information or products that EU can provide? Then we have mapping and monitoring of price growth using SAR data. Different research in the last 20, 30 years show that the C-band SAR, Sentinel-1, dense time series, the most effective. So we have a multiple result at local scale and larger scale. We are demonstrating with the project ESA project GRAS. And the second one is that we need to map the inundation status of the rice field. C-band cannot penetrate into the rice when the plants are fully developed, but N-band SAR penetrated through. So we should use the N-band SAR to do that. And currently we use ALOS-2, PALSAR-2, but with the 42 days repeat cycle. And because of that, we need also to combine with modeling approaches to assimilate the N-band SAR data for water level dynamics. And for methane emission, we need to use a process-based model for estimation with input from N and C-band SAR data. Here is some result of the GeoRise. It's going on project with ESA, CESGEO Global ESA. Here you have the website for that. And we have done the demonstration over here, Vietnam, Cambodia, Laos, Thailand. Here you see dry season 2018. And we implemented on GIAS Sobru in the last few months. And here the wet season 2018. And here when we have wet and dry season, we merge together and we compare with statistics from FAO and USDA. And here is quite good for the 3 countries, but for Thailand is we overestimated maybe the season, the definition of the dry season is not exactly the same at FAO, so we have to look again. And here the dry season 2019. And after that, we have done now recently 5 countries, Myanmar is adding. And here some detail of Vietnam, Central Vietnam, South Vietnam, Laos, Cambodia, Myanmar, Thailand. So the resolution is 10 meters. And here we have other products for Vietnam. Why for Vietnam? Because we got in-situ data, and for the other countries, it was difficult to get the in-situ data. And here is the single crop, double cropping, and triple cropping, quadruple, because it's for 1 year, and so it's for 3 crops and a half, something like that. So it's we can do it for the whole of Vietnam. And here is the phenological stage at each of the days of the Sentinel-1. And here in a product which is interesting is a long cycle and short cycle rice. And we know that the long cycle rice, people practice the continuous flooding, and short cycle rice, AWD. So by having the map of here 20% of the area for long cycle rice, and here we can have an approximation. If we take all the hectare of long cycle rice and we do it AWD, and then we save 40% of the methane emission for the Mekong Delta. And so you have this amount for 1 season. For 3 seasons, it's a 450 kiloton of carbon equivalent. So for the C-band, for Sentinel-1, we can follow the rice flow. And for the N-band ALOS-2, we can also have a map of rice field here. It's with SCANSA 100 meters resolution. We can have 1, 2, 3 data for 1 season. And here the map, but we cannot do the monitoring. But the advantage of using the C-band here is that we can look at the status of inundation of the under layer of the rice. So here experimental field, and here high resolution ALOS-2, and you can see the AWD or continuous flooding, white pixels are non inundated. And then if you go to larger scale with SCANSA, you take many SCANSA observation scene, you do the synthetic view, and you can have here continuous inundate, statistically inundate, statistically non-inundate, and in between is AWD. Like here you can see that submerged and non-submerged rice pixel can be detected by ALOS-2. But here for since the ALOS-2 is for 42 days, you need to have assimilation techniques to derive film water dynamic. Here the work is ongoing. Here from PALSAR data for data assimilation and for modern simulation. Here simulation using also the Sentinel-1 and other products from Opticon and then raw data for validation. You derive the film water level, you simulate it, and this film water level can be used for the farmer community to declench the irrigation operation. Here you can see the example for two of the sites for the simulation of film water level, and here is the comparison with the raw data. It's a 5 site, 5 plot, and 10 season. And for the methane emission, what we need is to have a process-based model. The process-based model could be also radiant estimation or greenhouse gas and water estimation. Here we use the DNDC, denitrification and decomposition model. And we have here input data, the climate, soil properties, and crop management. And the crop management can be here derived from Sentinel-1 for crop rotation, crop calendar, growth stage, and from ALOS-PALSAR we derive irrigation. Fertilization we cannot do. And here the output could be the yield, greenhouse gas, in particular methane emission, water demand. And we did some initial demonstration of methane emission using the NDC with input from Sentinel-1. And for that, the irrigation, we use the raw data. And here we can check that the NDC with Sentinel-1 is okay. Now we have to merge the irrigation from ALOS-PALSAR. And the initial demonstration from Japan also is the daily methane from Moody's. And then now we have to merge ALOS-PALSAR-2 and Sentinel-1. As to summarize and conclude, so the AWD practices recognized to be a good option for mitigation of greenhouse gas emissions from rice field. It has a positive environment impact. It has adapted to climate change when we have water scarcity, ensure food security, preserve affordability of food. And the point 2 is EU can provide information on rice growth and field inundation status, all that are necessary for greenhouse gas accounting and for monitoring of food production. The point 3 is we have done demonstration using EU data, model, and in-situ observation, and all are doing ongoing research work, but no plan for operational purpose. And for us also, for the requirement for future space observation, will be for an advanced SAR with systematic acquisition and high temporal frequency beyond ALOS-4 and NISAR of 12-14 days repeat cycle. So I finished there. Thank you very much for your attention. Thank you.
Thanks a lot. Thanks a lot for presenting us this impressive piece of work with lots of different strands and underlining again the importance of the undisturbed radar signals for monitoring at a large scale. And maybe you also have second thoughts about potential operational purposes also in relation to the monitoring of the SDG goals. So far, I've seen there is no questions from the audience, but there is still opportunities when we have our 20 minutes after all the 4 or 5 presentations, and maybe we will have some additional questions at this point. So I hand over back to Hans-Jörg, and thanks again.
Thank you. Thank you.
Thank you, Bettina. So now introducing the 5th and last presenter of this first day of the conference. I will call on Laksa Filchev to give a presentation on the Copernicus use case Bulgaria, high resolution national crop map of Bulgaria from Sentinel data. Laksa, over to you. Please unmute. You are still muted.
Yes, I just have unmuted myself. Can you hear me? Can you hear me now?
Yes, we can hear you.
Okay. So you have already introduced me, so I'll just start with the presentation. So this is the short title of the presentation. We have started working with the national crop mapping for Bulgaria from Sentinel data 2 years ago when we decided to scale up from our previous experiences and trials on small test sites.
Laksa, could you move a bit closer to the microphone?
Okay,
your voice is a bit low.
Yeah, but I don't know how I'm gonna look.
Now it's good actually, if you keep this position.
Okay. Can you hear me better now?
A bit.
A bit, okay. I'll stretch a bit then the mic. Now, how it sounds?
It's better, yes.
Okay, thank you. So, we have done this due to the CAP monitoring requirements and the national statistics and of course in European-wide statistics for the agriculture and also with the relation with the crop rotation monitoring. Of course, our main aim of the study is to detect the main crop types in Bulgaria using the Sentinels. But we did face some challenges, such as to discriminate agricultural from other areas. We've got some large crop diversity. We have about 200 crop types and land use categories. Of course, as many others already presented, we've got to mosaic images and to composite them, which requires a lot of computational resources. And strangely for me, somehow in the final version of today's, let's say, agenda, it appeared that we've got the soil health somehow. So I decided not to object this, but to take it as an opportunity, and I dropped here a slide with regard to the soil health and food mission, which is already in the next program of for research and innovation prize in Europe of the European Union. Within the mission board, we have already defined 8 indicators to monitor soil health, which is more or less related with agriculture and crop types. And I have highlighted 2 of the parameters which are not directly but indirectly related with the crop types. These are the vegetation cover and landscape heterogeneity. I can speculate a lot about soil health and food mission here, but I'm just marking in this topic that is going to be of higher relevance in the next years to come. And the study area, of course, is the national boundary of Bulgaria. We have presented here the Purin land cover 2018 data sets, the agricultural areas. Due to the complexity of Bulgarian territory, especially into the agroclimatic conditions, we've got some 4 distinct regions in Bulgaria, one of which is almost like, let's say, Mediterranean type of climate. We decided to narrow down or to break down the territory into 4 categories using the Hershkovich classification from 1984. We've got a crop nomenclature which has 4 hierarchical levels land use type, group, subgroup, and crop, which are organized, as you can see, into 14 types, which are mixed up between the groups and subgroups, and also individual crops. It turns out actually that this is not a very well thought out classification scheme, and you'll see it in the results section that it needs further refinement. We used the EACS dataset from 2019, which is courtesy to the Ministry of Agriculture and Food, the Bulgarian ministry. So we decided to split the dataset into 70 to 30. You can see here the training and the validation polygons used. And here is the workflow of our work. Basically, we have the EACS as an input. I already mentioned that we reclassify the layer, and we got a random sampling within the intersection of the Kurin 2018 and agro-climatic regions, which are the different study areas. Then we mosaic the regions and we produce the crop map. In the Google Earth engine, we mosaic the Sentinel-2 and Sentinel-1 datasets using these, let's say, parameters. And you can see that both composites are going into the classification process. Of course, afterwards, we've got accuracy assessment and accuracy assessment report. The main results are presented here of the image mosaics or the composites. You can see that these are bi-monthly composites from March to April, June to July, and August into September. These are for Sentinel-1 and Sentinel-2. These are some insets from these maps showing how they look in a, let's say, a little bit of zoom in window. And the end product for the crop type for 2019 is presented on these slides. You can see the 14 crop types, and what's apparent even from the first site is that we've got some issues for the smaller field size. Here are some examples from areas with, let's say, some bigger size of the fields, where the classification performs better. In the area of Dobrich, we've got a little bit more of issues because of the, let's say, smaller field size. And the worst result we have received in the vicinity of Plovdiv, where the paddies are really small compared to the pixel size, so we've got this type of patchy pattern. The overall accuracy with these 14 crop types, it's a little bit mixed up. As you can see, we've got good level of accuracy, producers and users, if we talk about distinctive crop types. But when we group them into, let's say, using their practice, such as the technical crops, the forage crops, etc., we've got a very low level of accuracy. We have noticed that despite the good agreement with some of the classes, we need still to check out whether the EACS statistics and other national statistics, which you'll see later, agree with our classification results, with our area estimates. And here is a comparison with the EACS dataset. Overall, we have an overestimation in almost all of the classes. And when we use the sampling statistics, which is performed on an annual basis by the Ministry of Agriculture, Food and Forests, we've got the same picture here. So we've overestimates the estimates of the Danish statistics. The main lessons learned is that the main crop types, as you have seen, are well distinguished, they are well discriminated. The crop groups, however, as defined in practice, such as the technical, forage, etc. Types, are not accurately mapped, so they have to be broken down. More homogeneous groups should be defined based on phenology, as we have seen in other presenters already. In the regular, let's say, user of the Google Earth engine, we encounter a lot of limitations, so we have to make trade-offs, such as the number of the classes, the training sample, etc., in order to break down the task into subtasks. And of course, the cloud masking is still problematic for Sentinel-2, as almost everyone has mentioned who has used this type of data set. And last but not least, still Google Earth Engine is a good tool for the national crop type mapping. Thank you for your attention.
Thank you very much, Laksa, for this interesting presentation of the use case in Bulgaria, and also explaining how you are expanding, let's say, improving thematic accuracy and increase accuracy in further steps. There are no specific questions at this point of time, but as we are at the end of the 5 presentations, there is more to think about. And asking questions in the general debate. So introducing the general debate, I mean, you heard a lot of interesting presentations, but also keeping in mind that we are at a point of time, let's say, of programming, for example, Horizon Europe, and also in view already of the 5th day, the Friday, thinking about, let's say, maybe future challenges and what could be, let's say, of interest for fine-tuning programming of Horizon Europe, but also the Agriculture of Data partnership. I would like now to hand over to my co-chair, Bettina. Maybe any of your thoughts for the final discussion?
Yes, thanks. Before we come to the final discussion, one question popped up, namely, what was the exact role of the Korean land cover data in the processing workflow?
I have started already typing in the answer, but anyway, I'll answer straightforward. Well, we use it mainly for masking out the rest of the areas, because we didn't want to mix up with other classes, from land use especially, and for these main purposes. Of course, it has some error in it. It's not flawless, the Korean 2018, but still it's, let's say, a nice approximation of the agricultural areas.
Thank you. So we conclude on this one, and I also would like to thank all the 5 representers and presenters very much for the excellent presentations. I think we've seen impressive classifications and impressive examples on how we can nowadays monitor agricultural practices in relation to CAP monitoring, in relation to mitigation measures and forth. But we have also seen the importance of ground truth data, be it statistical survey as LUCAS or be it the farmer's application, to really make use of deep learning and artificial intelligence. I now invite you all to give us some more questions we could ask. In the meantime, I would like to ask another question to Kenneth, our first presenter. You mentioned that you used the data also for the validation of the field boundaries, and I was wondering, seeing the data, Sentinel-2 Landsat, and giving the spatial resolution of the data, what your experience have been for updating field boundaries with this kind of data?
Yeah. So it's obviously on the 10-meter scale that we're working with Sentinel-2, and here we are using we're working with two different techniques. One is like classical segmentation of imagery, and that's been working. This has been ongoing the last year or two, and then we're also using deep learning technology for also segmentation. So there is some issues, of course, with the smaller parcels, but we can see, especially if we apply the deep learning method again and again on many Sentinel-2 images, that the borders of fields become more apparent. So there is some limitations, but again, this is the key. This question will keep on coming up with all types of applications when it starts pushing the capabilities of the imagery. So I do understand there's a lot of concern from other countries as well regarding this spatial resolution and parcels in general. For example, parts of Poland and Eastern Europe have very unique parcel structures compared to more in the west of Europe. They have very narrow parcels, and this is really another challenge that we have to deal with in the future. I'm not sure Sentinel can provide all the answers on that scale, but this is ongoing work, I think.
Okay, thanks a lot for your answer. A question a bit in the same spirit towards Pierre. I'm curious to have your view in how far you see the need of the Sen4 CAP system to be adapted to the specific country situation, and what's the kind of amount of work compared to starting from scratch?
I think the Sen4 CAP is actually providing metrics, which are, what we call the marker, which are very, very generic. And this actually relieves a lot of the burden from the user perspective. And he can focus on let's say, the selection of the most appropriate marker and the most appropriate threshold for his own application in his own context. Therefore, I would say that from year to year, we learn, and of course, we can adjust the parameters for a given country. But because of the Sen4 CAP machinery, which process as it comes all the data set with state-of-the-art, let's say, algorithm, I would say that this is a very generic solution, while the end of the let's say, application should be probably very much country-specific, also because of the specific regulation and specific challenges.
Okay, thanks a lot. Continuing a bit the control and monitoring of management practices, I was quite fascinated by the presentation from TUI, where we see that we have a measure which is easily controllable, can be easily monitored, and at the same time, we also see a good uptake by the farmers. And there was a question a bit earlier. Are you aware of any limitations for the adaptation by farmers of the alternating wet and dry pattern for the rice monitoring?
Yes, it's a very good question, because of the farmer, they are afraid of the loss of yield or the loss of production, so they didn't want to try. And so there's the government or local authorities ask them to try, few people try, and then the other follows. And so it's now it's the government say that we encourage in Vietnam, encourage people to do that. And there's some incentive for them to do that. There's no limitation. The first time that some researchers say that it's more N2O emitted, but later on they say that, okay, it's not much N2O compared to what happened before. And so now the incentive should be official by the countries, and then the farmer will follow. And then how to do that? We try to talk to nation, to people in every nation, that you can try it, and then there's no harm, and in contrary, save a lot of water. And so this no limitation.
Okay, thanks a lot, because I think that's the combination you are looking for, that you have an effective measure which is at the same time also controllable and monitorable, so that it can be in fact implemented from farmers' perspective, but also from an administrative perspective. I have a question here from Guido Lemort, and I think this is more targeted towards my ESA colleagues. So given the prominence of S1 in classification, what will be done to ensure a consistent European archive of level 2 data? Is there somebody feeling empowered to answer this question?
Yeah.
No, it doesn't look like. Then I go on to the next question. There was a question concerning the crop type classification. So this can be of interest to Raphaël, to LUCAS, but also to Kenneth and Pierre as well. And the question is, what was the biggest hurdle in the project of the crop type classification? So maybe we start with LUCAS.
Thank you. Well, for us, when we have started, as I mentioned 2 years ago, we have done some classifications using only Sentinel-2 data. So for us, it was about to combine the two data sets from Sentinel-1 and Sentinel-2. And the next issue, which we haven't faced about that time, was the scale. So we didn't approach national classification so far using such finer, let's say, spatial resolution data. And the third level of complexity or challenge was that the territory of Bulgaria turned out to be like a small Europe. We've got all of the issues here concerned with the different size of the crop of the fields, and also we have different agroclimatic conditions around the country. So more or less we've got all of the challenges, but I can't say that it wasn't a nice trip, and still is. And yeah, so to say, to sum up, these are the main challenges.
Thank you. Anybody else wants to add some challenges?
I can give you some experience from Denmark, maybe. I feel there isn't that much challenge actually now, technically. So, like, there is the data is there; it's very good. The algorithms are there, which are more or less, the top performing algorithms are good. The challenge I see beyond Denmark basically is with the training data and timely training data, and trying to have a transfer of models between years, or if we have place with different or with missing training data, that this can be the main challenge. That's my feeling on it. I think there's that being said, the data is out there, right, by paying agencies. They generally have the LPIS data on a timely fashion, but to create like a near real-time European crop type map I think it would be a really great advance if we could centralize this data and make it. I know there is Inspire and there's other initiatives to get this data more accessible, but I still feel that it's not there. It's not as far as it could be. Yeah.
Okay, maybe another question that relates to this kind of ground data and test data towards LUCAS. So I've seen here in the chat the question whether it would be not important to improve the representativeness of LUCAS with respect to scale and with respect to space and time. So this assumes that it's not representative in terms of space, which I would put a question mark, but surely maybe in time. Raphaël, are there any thoughts?
Well, I think it's a very good question because but unfortunately I don't have the answer, but I think it's related also to what we discussed just previously. Is that, I mean, we can what we need is having harmonized in-situ data that are open and usable for any scientist and administration. And I think there are several ways to move this forward. LUCAS is only one way, basically. It's a trick of using a statistic survey for Earth observation and to demonstrate that it has a potential and added value. No, I think that was the goal of our exercise. But at the same time, we have all this data, the parcel data, which are becoming open in some of the countries. I mean, you are aware that there is this initiative to share it and to have this open, but also they were designed differently. The legends are different. So anyway, you need to have a kind of work, and it's a dirty work basically because you spend a lot of energy to do this. No, but it's really needed. But yes, also we've done some experiment with using crowdsourcing. Well, there are many ways of this, but for sure that most of the money is going for developing fancy deep learning methods. Well, I'm sure that if we use deep learning method on this, we could reach a bit the higher results. But if I have some money, I would maybe invest more into having consistent, high quality in-situ data. But for this also, we have to find something that is in agreement with the need of different users, which is usually difficult. But I mean, I don't have a solution for this, but for sure, I think we should coordinate it, and probably at the European Commission level or ESA. I know that there are several initiatives. The Copernicus in-situ also probably should play a role there for the agricultural part, but well, it's a bit out of my hands.
Okay. Hans-Jörg, you want to say something for the data on agriculture in this context?
Maybe just generally, I think these ideas, these messages are very important for the co-design of the agriculture of data initiative, and taking, let's say, latest technology in, let's say, a deep learning algorithm development, bringing actors like paying agencies and research institutions, including, let's say, commission services around the table. This is one of the big opportunities. And the, let's say, co-drafters of this agriculture of data initiative, Marian van Mierlo and Doris Marquardt, they will be in the Friday session. So I think it's a good opportunity. I think that they know about these messages, and I will convey it also to them, so that there are opportunities. The partnership will only be rolled out in 2023. That means, but it means next year will be quite essential in programming it. So I think there are opportunities, and it's up to us all to use these. Thank you. Back to you, Bettina, I think, for continue co-chairing the questions coming up.
Exactly. I see another question here, open question from Pierre Defourny. Beyond the monitoring of agricultural practices, it would be great to look also at the impact indicators or impact of agricultural practices as TUI, very nicely completed for rice, CH, methane emissions. What would be the first indicator to target at? I assume you mean in Europe here, or generally, or to monitor the SDGs, or at what kind of framework are you looking?
Europe will be already fine.
But I see that water, irrigation water is something that need to be looked at. But I think that the works are ongoing for that, because there are a lot of irrigated crops in the south of France, and now we need to think very hard about all the indicators that show that there will be a scarcity of water in the next years. Okay.
And besides this, for the new CAP proposal, there is also the monitoring and evaluation framework where we will have, or where there will be different categories of indicators, amongst which you also have impact indicators, where some of this is also targeted at, and it's also research also to some extent is going on about the role of Earth observation for this monitoring framework. There was another question now to LUCAS relating to your classification. It's great that you have accounted for the agroclimatic zoning, and what was the impact of this data set on the classification policy?
Thank you for the question. Well, to be frank, I have to mention that we've got our inspiration from here and there. About the time we started the work, we already have checked out the literature and the experience of other teams, such as the SAN4CAP. So we already know and try to use SAN4CAP in our work. So we know that in this system, there is such type of preconditioning, let's say, before the classification. So we have tried to employ in our classification approach with the Google Earth Engine. But what's more flexible with the Google Earth Engine is that we can modify our workflow according to our end result. So it's more about trial and error. But let's say with regard to agriculture, with regard to the agroclimatic zoning, we have different areas in our country which, let's say, have different phenology. Of course, this type of zoning is defined as such depending on the phenology of the crop types. So it actually turns out to be improving the classification with 2 to 3%, not very much, but at least it's something. So these are the main benefits, especially in our case.
Thanks a lot for answering these questions. At the moment, I don't see any other questions, and I would like to bring to your attention that after the closure of this session, there's a requirement chat box open, where for 1 hour there will be also questions and answers and a possibility for the people participating to network and to place their requirements, which could be also an interesting format to further exchange. Hans-Jörg, anything else from your side?
No, I think nothing specific beyond what I mentioned already. Yeah, we are just 6 minutes before closure, so there is more opportunity actually to ask questions. But it's the first afternoon of this conference, and unfortunately we cannot deepen our discussion over a glass of wine in Frascati. But maybe there will be more opportunities next year and the years beyond for real meetings again. I mean, as Bettina pointed out, the chat during the whole week is an opportunity to reflect more. And maybe from my side, final words, I would like to thank all the presenters for great presentations, and I think really a cutting-edge science put in place to use the new opportunities of data available from Copernicus. I think for the next CAP period, there are huge opportunities actually that the common agricultural policy can live up to the Green Deal and farm to fork expectations by the work which you presented actually. Bettina, over to you for some final concluding words.
Yes, thanks a lot. First of all, I'm grateful that the IT didn't let us down. I also would like to thank the ESA staff, which is in the background, to nicely organize everything. I think it went all smooth, and we had some fun doing the session. I enjoyed very much listening to the 5 talks, and I found it incredible, the amount of evolution in the sector over the last 3, 4, 5 years. Today, I think we saw 3, 4 European-wide classification, a full classification of the Mekong Delta at parcel level. We can aggregate, we can work at different scales. So this is all quite amazing, I have to say. Applications are on the cloud. We can transfer applications, so we gained a lot of transparency in the sector. And I think this is really important to continue with these transparent approaches so that a lot of people can benefit from work which has been done, and we see this increasingly. So in this sense, I would like to thank everybody, thank for the excellent organization, and we close 4 minutes before time. This is also something I think which happens only virtual. In life, I think I never have ever close the session 4 minutes before we reach the official end. Thanks a lot to all of you, and I guess we see us again back in several of the other sessions this week.
And please use the chat opportunities which continue. Bye-bye.
Thank you.